So in definition number 1, we have the arc length formula. If a smooth curve with parametric equations, x is equal to f of t, y is equal to g of t, where t is in between a and b, is traversed exactly once as t increases from a to b, then its length is the following. L is equal to the integral that goes from a to b, the square root of dx over dt squared, plus dy over dt squared dt. Now for example number 1, we want to find the length of a parametric curve. We find the length of the arc of the curve, x is equal to t squared, y is equal to t cubed, that lies between the points 1, 1 and 4, 8. And here's the figure. So here we have our point 1, 1. We have our point 4, 8. We know that x is equal to t squared. We know that y is equal to t cubed. Now, we need to find out what those points are from a to b. In order to do that, we need to plug in our point here. We know that x is 1 and y is 1. So, excuse me, if we plug in 1 and square it for the x variable, 1 squared is 1. So we know that 1 was going to give us 1. If we put in 1 for y and cube that, we're going to get 1 cubed. So we know that we're starting at 1. And then for the other coordinates, we're going to get 4 and 8. So what values of t are going to give us 4 and 8? Well, if we plug in 2 for t and square it, we get 4. If we plug in 2 for t here for y and cube it, we get 8. So therefore, we know that a is going from 1 to 2. Now, since we noticed that, we now can then use our formula. We know that L is equal to the integral that goes from 1 to 2, the square root of dx over dt squared, plus dy over dt squared. So here is the first part. We're taking our integral from 1 to 2, and what is the derivative of t squared? Well, it's 2t, and then we're going to plug it into the formula to square it. Plus, what's the derivative of t cubed? What's 3t squared dt? Now we raise it to the second power, and we end up with 4t squared plus 9t to the fourth, taking the square root of that dt. And then ultimately we get the integral that goes from 1 to 2. Now we can factor out a t because the square root of t squared is in both terms, so we end up getting t times the square root of 4 plus 9t squared dt. And then we will go ahead and do our u substitution. We're going to let u equal what's under the radical, which becomes 4 plus 9t squared. And then the derivative of that is going to be 18t dt. Now, we need to determine what u is going to be by plugging in t is equal to 1. So we plug in t is equal to 1. So 4 plus 9 times 1 is going to give you 13 for the lower limit. And then if we plug in 2, we get 2 squared, which is 4, times 9, which is 36, plus 4, which gives you 40. So now what we have is we have an upper limit of, and we also have, if we solve for t dt, well, that is 1 over 18 du. So we can factor out the 1 over 18, and now we have the square root of u du. Taking the antiderivative of that becomes 1 over 18 times 2/3 u to the 3/2 with a lower limit of 13 and an upper limit of 40. And then we go ahead and then evaluate according to the upper and lower limits. And then we would get the result of 1 over 27, 80 times the square root of 10, minus 13 times the square root of 13. Now we can go a little further to figure out what that approximation would be, but that is our result. And as a check on our answer to example 1, we would notice that from that figure that it ought to be slightly larger than the distance from 1 to 1 to 4 to 8, which is approximately 7.615773. Now, according to this calculation in example 1, we end up getting approximately 7.633705. Therefore, it is a bit greater than the length of the line segment.